The problem of the points.
A and B are playing a game in which each of them put 50,000 VND in a pot, and the winner will take 100,000 VND. They flip a coin, and if it is head, A wins a point. If it is tail, B wins a point. The first to get 10 points will be the winner. At 8-7 with A leading, they have to stop the game as A's mother calls to ask her to go home. So, they decide to divide the prize based on the probability that each can win the game. How can they split the prize? Their reasoning is that at 8-7, the game will end in 4 coin flips. The game can end in 2 or 3 flips as well, but for sure the game will end in 4 flips. There are 16 equally likely outcomes of 4 coin flips. If there are at least 2 heads, A will win. Therefore, the probability that A will win the game is 11 out of 16. This means A is awarded 68.75% of the prize. The remaining 5 cases will be the victory for B, and she will be awarded 31.25% of the prize. But this approach has a drawback that they use counting. What if the number of points involved is large? We now discuss the ideas that are brought up in the example. As indicated above, 2 players, A and B, contribute equally to the stakes and then play a series of points until one of them wins T points. The probability that player A wins a round, 1 point in each round, is P, and the probability that player B wins a point is 1 minus P. Suppose that the game is stopped for some reason before either player has won. At the time of stopping, player A has won A points and player B has won B points with A less than T and B less than T. Let N equals T minus A and M equals T minus B. The key to solving the problem of points is to look at an extended play of N plus M minus 1 points. Here's the great insight that came from Pascal and Fermat. They looked forward and not backward. They did not base the solution on the number of points that are already won. Instead, they focused on an extended series of points to determine the share of the winning. This additional play of points is fictitious, but it helps clarify the process. In essence, they turned the original problem of points into a problem about this additional play of N plus M minus 1 points. The original problem is, what is the fair share for player A when the game is stopped prematurely with player A having 1 A points and player B having 1 B points? The equivalent problem is, what is the probability of player A winning at least 10 points of the next 10 plus M minus 1 points, where N equals T minus A and M equals T minus B, assuming the game has not stopped? Let's call this probability P. The 10 successes occur before M failures. Let's examine the setting of this probability. Each point is either a success, player A winning it, or a failure, player B winning it. There are N plus M minus 1 trials. The probability of success is P in each trial. We wish to find the probability that there are at least N successes. The probability being sought is like this. Where N equals T minus A, M equals T minus B, and that A is the number of points won by player A and B is the number of points won by player B at the time the game is terminated. This is called the method of binomial distribution. The problem of points, also called the problem of division of the stakes, is a classical problem in probability theory. It is not only the first major problem of probability, but it is also the one responsible for its foundation. There are 2 celebrated problems in probability that originated from the French professional gambler Chevalier d'Aumire. One of the problems posed by Chevalier d'Aumire to Pascal, the dice problem, and the second problem is the problem of points. The problems were solved jointly by Blaise Pascal and Pierre de Fermat in a series of letters. The ideas discussed in these letters were often credited with having started probability theory. Pop had such an impact that almost all major probabilists from then on, from Huygens to Laplace, had a say on it. Their solutions to this problem would open up new doors in mathematics and other fields. As one of the famous problems that motivated the beginnings of modern probability theory in the 17th century, it led Blaise Pascal to the first explicit reasoning about what today is known as an expected value.